So when we're talking about heat transfer, we're going to talk about characteristics of materials and and a way to describe them. Engineers have come up with ways to describe certain types of materials, and a U value in this case is called the coefficient of heat conductivity, and it's the measure of a material's ability to conduct heat. So it's the measure of a material's ability to transfer heat from itself, like by touching. Remember, conduction is by like touching, and it's a characteristic of a material. So different materials will have different U values. Those are the units there. There's also another characteristic when talking about energy transfer, thermal energy transfer, and it's called the R value, and it's the thermal resistance of a material. So the U value is the coefficient of heat conductivity. It's the how well the material can conduct heat, and then the R value, like resistance, the R value, how well it can resist heat. So how well it it resists being heated up. So like the heat shield on like a capsule on a rocket when you come back down, like Apollo 13, the heat shield is broken, it's cracked. That needs to have a really, really high heat R value, because it needs to be able to resist heating up. Something that's interesting about R value is when you compile certain materials, more than one material, like different materials together, you can just get the R value by adding them together. So the R value just adds together to get the total R value. Because if you're heating something, you have to heat it one layer at a time, so it just resists that amount of heat in that amount of time. So R values, if you're having like more than one material stacked up, then all you're doing is just adding the R values of those. You're adding the thermal resistance for each of those materials to get a total R value. That's what bulk R value means. So R value is the thermal resistance of a material, and then the U value is the coefficient of heat conductivity. And it makes sense that they're related, because if a material conducts heat very, very well, then it should have like a really low R value. It means like thermal energy can pass through. If you have a really, really high U value, that means you can have thermal energy transferred through whatever material very easily. If you can conduct, or if you can have the thermal energy transfer through the material really, really easy, then it's not going to be very resistant to heat, because it heats up so quickly. Hopefully that just makes sense. And the equations are related. Ooh, interesting. We're going to be actually building some type of insulation. You're going to be calculating all this stuff, I think. I don't know. We'll see. So an example of calculating R value, this is kind of silly, because we literally just said if you want to calculate the R value of a bunch of materials stacked together, you just add them up. So the total R value of this insulated, wall, this would be drywall fiberglass bat. It's not like a baseball bat. It's just like cotton candy, except if you eat it, your insides get messed up. Foil face poly, yes, okay. Air, ooh, look at that. And air has an R value. Actually, I think I'll give you a table of R values, or in your problems you'll always get the R values, or you'll be able to look them up. And then, the brick on the outside. Oh, this is the inside, this is the outside. So if you're calculating the R value of like a wall, then you're calculating its ability to resist heat, or to resist thermal energy transfer. So it's like you want it to resist very well, because if it's hot outside, you don't want it to be hot inside. You want it to resist that thermal energy transfer. Same if it's warm inside, you don't want it to seep out everywhere. So to calculate the total R value, you just add them all together. I'm just going to write it down. You're adding. That's it. So if we add the R value for this section would be 27.7. However, if we have the R value for this, it's different because, what does that say? 2x6 construction. That just means like there's a piece of wood in there to hold the wall together. So this piece has a different R value. So if you have, different parts of the wall will feel colder or warmer depending on, not drastically because we probably wouldn't be able to tell, but they have different R values. So the R value here would be, of course, let's do it in green. 0.56, that's this wall, or the drywall part, and then the R value of the wood there, that would be plus 6.88, and then plus the foil faced polyisocyanurate. That's a big word for me. All right. So the plus 7.20 plus the air, which is 0.17, and plus the 0.8. I like this one. And that's is a 15.6, 15.6. It's just a 15.6. So the different parts of the wall have different R values. You gotta be careful with this stuff, You just gotta take into account all these little different things. We actually already talked about radiation, but it's another way that thermal energy can be transferred, and it's transferred through electromagnetic waves. That's how the sun heats up the Earth. It's transferred through electromagnetic waves. Sweet. We do have an equation to tell us the net energy transferred through radiation, and it's this. So this formula will tell us the net energy transferred through radiation. The parts of this formula are Stephen's constant. I don't even know how to say his name. That's sigma. That's a Greek letter sigma. It's the lowercase sigma, I think. I was right. I just looked it up. And then A. What is A? A is the area that you're transferring through radiation. E is the emissivity. Sheesh. No, I said it right. Emissivity constant. Emissivity, yeah. And then T is the temperature. Ooh, in Kelvin. So when you're dealing with radiation, you have to use kelvins. Okay, that's interesting. And I'll stop this and make another video. It looks like Donald Glover from Community. No, it doesn't.